84.1 degrees Celsius on the Antarctic Plateau, while 7,000 kilometers to the north, Argentina recorded the hottest winter night in 101 years of observations. Same day, same hemisphere, and as it turns out, the exact same atmospheric machinery. 136.8 degrees Celsius. That is the gap between the absolute hottest and coldest temperatures measured across the surface of Earth this year, a spread wider than the gap between freezing and boiling water. On Saturday, the 18th of July, both ends of that global extremes index moved simultaneously. While a joint research base on the high Antarctic polar cap registered the lowest air temperature recorded anywhere on this planet since 2012, a weather station in South America recorded an overnight minimum that sat 23.2 degrees Celsius above its winter normal. To a casual observer scrolling through headline updates, these two events look like contradictions, or worse, arguments against one another. They are not. They are two distinct readouts of a single, highly compressed physical system. To understand why this happened, we first have to execute a necessary correction move. Headlines frame this as a bizarre climate paradox, or proof that global systems are behaving entirely at random. That loose framing completely misses the physical reality. What occurred on July 18th was not a random roll of the atmospheric dice. It was the direct mechanical output of an unusually intense polar vortex, a tight, high-speed ring of stratospheric winds that effectively sealed off the southern continent while altering the planetary wave train downstream. The accurate story isn't that Earth produced two unrelated weather anomalies on the same day. It is that one massive atmospheric structure organized the global plumbing to deliver both at once. Precision is the real engine here, because when you look at the exact numbers, the mechanics become impossible to ignore. At Concordia Station, a joint French and Italian research facility sitting at an elevation of 3,233 meters on the East Antarctic Plateau, the mercury plummeted to minus 84.1 degrees Celsius. At an altitude over 3 kilometers above sea level, the air above Concordia is exceptionally thin and contains almost zero water vapor. Water vapor is the atmosphere's primary heat-trapping gas. Remove it, and you effectively strip away the planet's insulation. Combine that thin, dry air with 4 continuous months of polar night, and the surface radiates heat upward into space endlessly without receiving a single watt of incoming solar energy in return. Under those specific conditions, the temperature doesn't just drop to a comfortable low. It cascades down toward the physical floor of what Earth's surface can produce. The only force capable of interrupting that plunge is the arrival of warmer, moist air masses from the mid-latitudes. But throughout July, those warmer air masses could not breach the continent. Something was holding the door shut. That barrier was the stratospheric polar vortex. Think of the vortex as a planetary-scale pressure lid. When the temperature contrast between the equator and the pole is sharp, the ring of westerly winds speeds up, tightening its grip and isolating the Antarctic air mass inside. In late July, the Antarctic Oscillation Index, the key metric used by climatologists and bodies like Natural Resources Canada to track the strength of this polar jet, surged to an extraordinary value of plus 5.0. An index reading of plus 5.0 indicates a polar vortex that is not merely present, but locked in an exceptionally tight, high-velocity configuration. The seal held. Cut off from any heat exchange, the high plateau cooled to levels not seen in 14 years, missing Concordia's all-time station record by just half a degree. At the exact same time, that rigid stratospheric setup was altering the flow of the jet stream further north. As the locked vortex anchored itself over the Amundsen Sea, it carved out a deep atmospheric trough off the eastern coast of South America. That trough acted like a giant mechanical pump, pulling warm, tropical air out of the continental interior and channeling it directly southward over northern Argentina. In the city of Salta, where the typical midwinter low sits around 3 degrees Celsius, the temperature never dropped below 26 degrees Celsius all night. That is an overnight minimum 23 degrees Celsius above seasonal norms, occurring in the dead of winter. It was not a localized fluke. It was the direct downstream consequence of the Antarctic pressure lid holding tight thousands of kilometers away. This brings us to the core mechanism that connects these extremes. The polar vortex does not generate temperature on its own. It arranges the planetary circulation patterns that decide where cold and warm air masses reside. When the vortex is locked, the extreme cold remains trapped at the pole, while mid-latitude wave patterns are forced into tight, persistent loops elsewhere. But when that vortex ring weakens or breaks apart, the system completely flips. Warm, moisture-laden air rushes poleward, cloud cover locks in, and the coldest continent on Earth suddenly experiences massive spike anomalies. The critical question this entire episode forces us to answer is straightforward. What happens when this massive atmospheric lid fails completely, and where does that leave the stability of our broader polar systems? Minus 89.2 degrees Celsius. On July 21, 1983, a spirit thermometer mounted at Vostok Station on the high Antarctic ice sheet recorded that number, establishing the absolute lowest surface air temperature ever measured on Earth. For 43 years, that single data point stood as the undisputed baseline for planetary cold, a physical floor against which every polar winter was measured. Exactly 43 years later, when newsrooms flashed headlines about Concordia Station hitting minus 84.1 degrees Celsius, public commentary immediately seized on the frame that Earth was reverting to an older, colder baseline. That framing is completely wrong, and setting the historical baseline straight reveals why the reality is far more concerning than a simple internet narrative. To understand how far outside normal operational limits our atmospheric machinery is currently swinging, we have to look at how these baselines were established in the first place. When Soviet meteorologists built Vostok in 1957, and when French and Italian polar agencies established Concordia high on the East Antarctic Plateau at an elevation of 3,233 meters, they were placing instruments in an environment defined by deep physical isolation. For decades, the historical record showed remarkable consistency. Planetary cold records required an exact alignment of factors: months of total polar darkness, high elevation, absolute absence of water vapor, and a completely unbroken stratospheric polar vortex. Under these classic baseline conditions, heat radiated out into space continuously, while the fierce ring of stratospheric winds kept any warmer maritime air from penetrating the interior plateau. For half a century, meteorologists at Environment and Climate Change Canada and international monitoring bodies viewed this polar isolation as an immovable constant. The Antarctic interior was considered a vast, stable reservoir of hypercold air, a region whose sheer thermal mass buffered it against rapid, short-term shifts. But establishing a true baseline requires separating remote skin temperatures from standard atmospheric measurements. Satellite remote sensing instruments scanning orbitally over the East Antarctic Plateau have occasionally detected surface snow skin temperatures between minus 93 degrees Celsius and minus 98 degrees Celsius. However, those are measurements of the top millimeter of snowpack radiating into space, not the ambient air temperature 2 meters above the surface where human instruments and human bodies operate. Concordia's minus 84.1 degrees Celsius reading was a genuine, calibrated air temperature measurement, and while coming within half a degree of Concordia's absolute station record sounds like an extreme return to historical cold, looking at the baseline arithmetic shows a very different picture. A cold event that fails to beat a 43-year-old planetary record by more than 5 full degrees is not evidence of a cooling climate. In fact, when placed alongside the historic baseline data, it marks a key transition point in how polar weather systems function. In the early decades of polar monitoring, the atmospheric boundary layer over the high interior remained relatively predictable. The cold air stayed locked over the high plateau, while mid-latitude systems circulated predictably around the Southern Ocean. The historic weather records maintained by national meteorological agencies, from the Geological Survey of Canada to the Argentine National Weather Service, which has logged continuous data since 1925, demonstrate that while local fluctuations occurred, the overall planetary circulation maintained strict boundary lines. Those boundary lines no longer hold their historical shape. The baseline assumption was that polar air masses stay confined to the polar caps, while subtropical systems remain within their expected latitudinal belts. In Salta, Argentina, where meteorological tracking goes back 101 years, the midwinter baseline for overnight lows in July was firmly established at 3 degrees Celsius. The sudden jump to an overnight minimum of 26 degrees Celsius on July 18th did not merely break a record, it shattered a baseline that had held stable across more than a century of standardized industrial observations. To put a 23.2 degrees Celsius positive anomaly in perspective for a Canadian audience, that is equivalent to a city like Calgary or Edmonton, where normal winter overnight lows sit around minus 15 degrees Celsius, suddenly experiencing a midnight temperature of plus 8 degrees Celsius in the middle of January. It is a value that falls entirely outside the design parameters of the historic climate record. By examining the historical baseline, we see that the individual numbers, whether minus 84.1 degrees Celsius in the polar darkness or plus 26 degrees Celsius in the South American subtropics, are not isolated outliers. They are signals that the underlying mechanism governing heat distribution across our hemisphere is entering a phase of extreme variance. The historical baseline was defined by stability through isolation. The emerging reality is defined by intense, rapid swings, driven by a stratospheric vortex that now alternates between impenetrable rigidity and complete structural collapse, including the advent of 30.9 degrees Celsius above normal. On August 5th at Dome Fuji Station on the Antarctic Interior Plateau, an atmospheric monitoring display registered an anomaly so massive that initial quality control filters nearly flagged it as an instrument error. It was not an error. At two separate research outposts, near-surface temperatures spiked over 30 degrees Celsius above the winter baseline in a matter of hours. That single reading marked the absolute breaking point of the polar containment system, the precise moment when the stratospheric engine failed, exposing the underlying physical mechanism that drives the most violent thermal swings on our planet. To understand the catalyst behind these extreme swings, we have to look past simple surface weather and examine the step-by-step physical mechanism operating 30 kilometers up in the stratosphere. Under normal conditions, the polar vortex is held stable by a strong temperature gradient between the warm tropics and the sunless polar cap. This gradient powers a screaming ring of westerly winds, the polar night jet, that acts as a physical boundary. Inside this ring, radiative cooling proceeds unchecked. As heat bleeds off into deep space, the air density increases, trapping an isolated core of hypercold air over the continent. This is the sealed configuration that produced the minus 84.1 degrees Celsius reading at Concordia. The catalyst that breaks this system does not originate in the polar regions. It begins thousands of kilometers away in the mid-latitudes and tropics, driven by massive energy imbalances. Enormous atmospheric waves, known to meteorologists as planetary Rossby waves, are generated by intense convective thunderstorm activity and temperature contrasts between continents and oceans. These waves propagate vertically, pushing upward from the troposphere high into the stratosphere. Most of the time, the powerful westerly ring of the polar vortex simply absorbs these waves, deflecting their energy. But when tropical convective activity becomes unusually energetic, the upward wave flux reaches a critical threshold. Instead of absorbing the wave, the polar vortex is forced to absorb more energy than its rotational momentum can maintain. The waves break against the vortex like ocean swells crashing against a seawall. When this energy transfer exceeds critical tolerances, the jet stream slows rapidly and undergoes severe distortion. In extreme cases, the wave flux causes a sudden stratospheric warming event. The ring of westerly winds weakens, buckles, and is pushed off its geographical center over the pole. In the most violent cases, the jet stream actually reverses direction entirely, shifting from westerly to easterly. When the vortex wall buckles, the pressure lid is blown wide open. The isolated cold pool trapped over the plateau collapses. In its place, high-pressure ridging forces warm, moisture-laden maritime air masses from the mid-latitudes to surge directly poleward. As this air ascends the interior ice sheet, atmospheric moisture condenses, forming dense cloud cover across regions that are normally as dry as the Sahara Desert. This cloud layer acts as a powerful thermal trap. Instead of the surface radiating its heat away into space, the cloud deck absorbs the infrared energy and radiates it back down toward the ice sheet. This sequence triggers a severe water vapor, cloud, and radiation feedback loop. Humidity levels in the lower atmosphere soar, and downward long-wave radiation spikes dramatically. This exact mechanism unfolded during the unprecedented heat wave analyzed in a benchmark paper published in Climate and Atmospheric Science by Dr. Hu-Su Tang and Dr. Sohan Lee. Tracking atmospheric data at the 10 hectopascal level, roughly 30 kilometers above the surface, the researchers documented eddy heat flux anomalies exceeding 4 standard deviations above normal, driven by a massive wave number 1 planetary wave. At the surface, the physical consequences were staggering. Across Dronning Maud Land, an area larger than Ontario, surface air temperatures remained more than 9 degrees Celsius above average for 17 consecutive days. Circulation modeling revealed that direct atmospheric transport accounted for 47% of the total warming anomaly, with the rest driven by local radiation feedbacks. The old predictive models, built on decades of historical baseline data, failed to forecast the sheer magnitude of the spike because they assumed the stratospheric vortex was an immutable barrier. The catalyst proved that when planetary wave activity over the warming oceans reaches a tipping point, the polar lid doesn't just flex, it shatters, transforming the coldest place on Earth into a site of unprecedented thermal spikes. For 21 consecutive days, dark rock lay completely exposed to the polar sky at the foot of the Collins Glacier, a site that should have been locked beneath meters of reflective snowpack in the dead of midwinter. On June 6th, Esperanza Base on the Trinity Peninsula reached a recorded temperature of plus 15.4 degrees Celsius. When dark, bare ground opens up in an environment designed to reflect 80% of incoming thermal radiation, the local surface energy balance flips immediately. Exposed rock absorbs solar and atmospheric heat, warms up, and radiates that energy laterally into the surrounding ice, accelerating thaw far beyond what ambient air temperatures alone would dictate. That localized feedback loop is where abstract stratospheric shifts transform into tangible physical destruction. To understand why this atmospheric volatility matters, we have to look at how these extreme swings cascade through real-world systems, infrastructure, and human supply chains. When atmospheric stability breaks down, it doesn't just produce headlines about isolated scientific research outposts. It alters the operational baseline for entire regions. Consider the scale. An Antarctic heat wave covering an area roughly the size of Western Canada, spanning Alberta, Saskatchewan, and Manitoba combined, means thousands of gigatons of ice mass are exposed to positive thermal anomalies simultaneously. When those anomalies cross the freezing point, as occurred on the Antarctic Peninsula this winter, the physical structure of buttressing ice shelves begins to degrade. The immediate real-world impact is not abstract sea level rise decades into the future. It is the instantaneous disruption of global weather teleconnections that govern seasonal stability across North America. When the polar vortex undergoes severe displacement, the global jet stream buckles into wide, stagnant meanders. For Canadians, this atmospheric setup is intimately familiar. It is the exact mechanical configuration that brought the catastrophic November 2021 atmospheric rivers to British Columbia, severing every major rail line and highway connection to the Port of Vancouver, or the 2021 Pacific Northwest heat dome that shattered national records at Lytton before a devastating wildfire swept through the town. When mid-latitude weather patterns lock into place, the real-world consequences hit critical infrastructure immediately. In northern communities that rely on winter roads, such as the Tibet to Contoido ice road supplying remote sites across the Northwest Territories, a swing of just a few degrees in seasonal averages shortens the operational window by weeks. Heavy transport trucks carrying fuel, building supplies, and equipment can no longer safely cross ice bridges that require sustained deep freezing to maintain structural integrity. A shortened season forces resupply onto expensive air transport, instantly driving up the cost of food, heating fuel, and municipal services for northern residents. Similarly, rapid thermal swings directly jeopardize Canada's water security and hydroelectric generation networks. Hydrological systems managed by BC Hydro, Manitoba Hydro, and the International Joint Commission depend on predictable seasonal melt cycles. When midwinter warming events strike glaciated headwaters like the Columbia Icefield or the Athabasca Glacier, premature runoff disrupts reservoir management. Water arrives months before municipal and agricultural infrastructure is prepared to store it, threatening downstream supply along the Bow River and across the Canadian prairies during the critical summer growing season. In urban centers, extreme atmospheric volatility strains power distribution networks to their design limits. During severe cold snaps driven by vortex displacement, electrical grids managed by Hydro-Quebec and provincial utilities experience unprecedented demand surges as heating loads spike simultaneously. Conversely, rapid unseasonal warm spikes push cooling demand past summer peaks, risking localized transformer overloads and rolling brownouts. Across transportation corridors, freeze-thaw cycles happening in months that should be continuously frozen destroy pavement, trigger rockfalls along mountain passes through the Rockies, and increase the risk of massive thaw slumps in permafrost zones, threatening pipelines and highway foundations from Tuktoyaktuk to the Yukon border. The real-world impact of these polar atmospheric disruptions is not a distant future threat. It is a present operational challenge that is already reshaping public safety alerting via Public Safety Canada's Alert Ready system, altering municipal disaster planning from coastal harbors to prairie municipalities, and forcing insurance providers to recalibrate risk models across North America. The machinery in the upper atmosphere has demonstrated that when its balance shifts, the structural integrity of our daily infrastructure is what absorbs the blow. It's the 2.58 million square kilometers. On February 26th of this year, satellite monitoring recorded that figure as the annual minimum sea ice extent surrounding the Antarctic continent. It was the 16th lowest reading in the 48-year satellite record, a partial recovery after 4 consecutive years of severe deficits, but still well below the long-term climatological baseline. In an era of sensational headlines, that single number encapsulates the honest, complex reality of polar dynamics, a mixed picture that resists simple alarmism while signaling a structural shift in how our hemisphere distributes heat. What is clearly established by peer-reviewed research, including the Hu Su-Tang and Seohan Lee analysis published in Climate and Atmospheric Science, is that anthropogenic warming has altered the baseline against which these polar atmospheric events occur. Human influence did not cause the polar vortex to exist, nor did it invent planetary wave activity, but it has doubled the likelihood of extreme winter heat waves across the Antarctic continent. Under moderate emissions scenarios, climate models project the frequency of these stratospheric breakdown events to rise to 6 times their historical rate by the end of this century, and up to 26 times under high emissions pathways. What remains genuinely unresolved is whether the frequency of the atmospheric circulation pattern itself is changing. The data currently shows no robust, statistically significant trend in how often the stratospheric vortex experiences these sudden warmings or rigid locks. The swings themselves are not necessarily happening more frequently. Rather, because the background thermal baseline has shifted upward, when a breakdown occurs, the resulting surface temperature spikes land much further into unprecedented territory. Furthermore, despite extreme winter warm anomalies reaching over 30 degrees Celsius above average in the interior, temperatures across the high polar plateau still remain far below the freezing point. The interior ice sheet is not on the verge of sudden, catastrophic melting overnight. To track where this system goes next, there are 3 specific, checkable metrics you can monitor in real time. First, track the Antarctic Oscillation Index, published continuously by atmospheric monitoring bodies. A sustained surge above plus 3.0 indicates a locked, hyper-intense vortex that bottles cold air over the pole while driving extreme temperature patterns across southern continents. Conversely, a sharp drop into negative territory signals a weakening vortex ring and potential wave-breaking events. Second, watch the seasonal bulletins issued by the Canadian Ice Service and international polar agencies regarding Antarctic sea ice growth during the austral winter. If winter ice growth fails to recover toward the long-term median, the reduced surface reflectivity will allow ocean waters to absorb more thermal radiation. Third, monitor reports from coastal research stations like Esperanza Base on the Antarctic Peninsula for multi-week midwinter melt events, where ambient temperatures cross the 0 degrees Celsius threshold. Until one of those specific developments shifts the baseline, the current situation is best understood as a period of heightened variance within an increasingly energetic global atmosphere. The planetary engine isn't breaking down at random. It is operating with higher thermal amplitude, producing record cold when the stratospheric lid locks tight, and record heat when it shatters. The true danger isn't that Earth is becoming unpredictably chaotic, but that the atmospheric machinery governing our climate is demonstrating just how violently it can swing when pushed past its historical limits. Tell us in the comments below where you are watching from today. Subscribe to stay informed as we continue